Hi, my name is Julie Kallini, and I am a computer science PhD student at Stanford University, and I'm excited to be talking about our paper, Mission Impossible Language Models. I want to give a big thank you to my wonderful co-authors. Just a few months ago, there was a short correspondence in Nature that made 3 big claims about why AI doesn't model human language. I could talk at length about each of the claims the authors bring up, but I'm going to focus on this third one. Here, the authors state that large language models can produce impossible languages, or those not generated by the principles governing all known human languages, just as well as, if not better than, natural language output, and cannot distinguish between them. Similar claims have been made by several linguists, including Noam Chomsky in his New York Times article from last year. For these authors, LLMs learn possible and impossible languages equally well, and so it follows that LLMs do not model the structure of human language and cannot tell us anything about language. This claim, if true, would have significant consequences for linguistic methodology, and potentially also for the viability of LLMs as the basis for robust language capabilities. What we set out to do is actually put this claim to the test. We trained some language models on impossible languages and tried to observe whether they are learned just as well as the possible languages. But first, you might be wondering, what exactly is a possible or impossible human language? Well, this question lacks a very clear answer. If we take the characterization of language as it is presented in much of theoretical linguistics, then all human languages are thought to have hierarchical structures, syntactic structures generated through recursive rules. And we could represent these sentences through these hierarchical syntax trees. So if we grant that the possible languages are defined by these hierarchical structures, what are the impossible languages? Well, these would be languages that have the opposite type of rules, or rules that are not hierarchically structured. More concretely, these rules are based on the linear order of words, or rigidly determined by word positions. So if we take the same syntax tree I showed before, we can make an impossible language by introducing a rule that violates the hierarchical structure of sentences. As an example, we can look at how tense is marked in this sentence. It is marked by an S suffix on the verb. What if the way English marked verb inflection was by placing the tense marker a fixed number of words later? This would be a completely systematic pattern, but no language uses counting and inserting markers in this way to signify verb inflection. It's a completely unnatural pattern. What I just showed you was an example of a language that involves linear counting rules, but I think that this is a narrow account of what is impossible. In our paper, we test on a much wider range of impossible languages and place them on a scale we call the impossibility continuum. We know that the real languages in the world are possible for humans to learn by definition, and they are hierarchically structured. The languages involving count-based grammar rules like the one I've shown are close to the attested languages, but they include rules that do not conform to the hierarchical structure of attested languages. Beyond these languages, we also test languages of reverse strings and languages with shuffled word orders. And in constructing these impossible languages, we consider both their information theoretic attributes relevant to machine learning, as well as their formal linguistic characteristics. And we signify the boundary between possible and impossible with a question mark to indicate that these distinctions are currently fuzzy. Our methodology could be used to explore this boundary for LLMs. So how do we test whether language models reflect this impossibility continuum? In our experiments, we create synthetic impossible language datasets by altering English data. For the base corpus, we use the 100 million word BabyLM dataset. And then we train a GPT-2 small model from scratch for each synthetic dataset. These models are not pre-trained, and they've only seen data in the impossible language. Then we use test set perplexities as a general metric for the extent to which a model has learned an impossible language. In the paper, we group the languages into 3 classes based on the continuum I had shown previously, and we call these the shuffle, reverse, and hop languages, where the hop languages are the count-based languages I motivated earlier. And these are the perplexity plots across model training steps for all of the impossible languages. I won't be able to go into each of the languages here, but I want to draw your attention to the bottom lines on each of these graphs. These are the control languages that represent unaltered English, and in all cases, the natural control language had lower perplexities than all of the impossible languages. While there are clear distinctions for the shuffle and reverse classes, the distinctions among the hop languages are pretty subtle, so we will be taking a closer look at these languages with a more targeted evaluation. I want to first detail how the hop languages are constructed. First, no hop is the control language, which represents English, but there are a few preprocessing steps we take to make this an adequate control. First, we lemmatize all third-person present tense verbs, so in this sentence the verb cleans is changed to clean. Then we insert a marker representing the verb's tense and number right next to the verb. This isolates verb tense and number into a single marker. Then finally we tokenize the sentence. In these examples, differently colored blocks represent different GPT-2 tokens, and the verb marker is represented by its own token. Next we have the token hop language. Here we pre-process the sentence in the same way, but this time we insert the marker exactly 4 tokens after the verb. Finally, in the word hop language, we do the same thing, but this time we insert the marker token 4 words after the verb. So you can see that this time the marker respects word boundaries. So how can we better test whether GPT-2 prefers the more natural control? We next devise an experiment that uses surprisals to measure how well each of the hop models can predict the placement of its verb marker tokens. What we want to know from this experiment is, first, whether each hop model learns to expect verb marker tokens at the correct locations, and second, how surprised is the model when verb marker tokens do not appear when they're supposed to. And what we do is create these pairs of grammatical and ungrammatical sentences in which the verb marker token appears and does not appear. And then we can get the surprisal of the verb marker token in the grammatical construction, and the surprisal of the token after it in the ungrammatical construction. If the hop model has learned its respective verb marking rule, then the surprisal of the verb marker in the grammatical constructions should be small, and the surprisal difference of the verb marker and the token that follows it should be large. We take a sample of test sentences and measure the mean marker surprisals and the mean surprisal differences for each of the hop models over training steps. So again, these are the 3 hop languages for reference, and here are the results for the first surprisal experiment. The left bar in each graph is the control model, and you can see that it has the smallest marker surprisals across all intervals of training steps. Both of the impossible languages have higher marker surprisals, but interestingly, the token hop model does better than the word hop model, indicating that GPT-2 is better at learning the counting rule when the unit being counted is a token. And this result is also supported by the surprisal difference metric. The control has the largest surprisal difference across training steps, followed by the token hop model. So, based on the results of these surprisal experiments, GPT-2 favors the natural grammar rule, but it is also capable of acquiring a count-based grammar rule. I won't have time to go into it here, but our paper includes a deep dive into the internal mechanisms of the hop models using causal abstraction analysis, so you can check that out if you're interested. With these results in mind, I want to return to the motivation I had at the beginning of the talk, and ask, do LLMs learn possible and impossible languages equally well? In this work, we show that GPT-2 can distinguish between possible and impossible languages, challenging previous unfounded assertions about LLMs. And more importantly, this work shows that LLMs can tell us a lot about language, complementing and defending a rich line of work showing that LLMs can learn syntactic or more general linguistic principles just from data. Since we found that GPT-2 had an easier time learning the possible languages, this leads to the question about what inductive bias does GPT-2 have that matches natural language? We make the argument that it has to do with information locality, or the property that, when parts of text predict each other, they are often close together. And a preference for locality arises in GPT-2 due to the incremental nature of its causal language modeling objective. We see this work as a call to action for research and architectures with different inductive biases that may be even better than GPT at finding the possible versus impossible distinction. To conclude, our paper opens up a new question about how LLMs can help us identify possible or impossible languages and bring us closer to defining the boundary between these 2 classes of languages. And we have made the case that LLMs are clearly relevant to investigations and claims about language learning and can be used as a tool for exploring questions like what can be learned from data, or what sorts of innate priors are necessary for language learning. Arguments that, by design, they are unlimited in what they can learn or incapable of distinguishing the possible from the impossible do not offer convincing evidence otherwise. Thank you.